Welcome students. Today we're going to discuss notes 12.1, which are solids, three-dimensional shapes. And today what I'm going to do is I'm going to show you a picture, I'm going to give you a definition, and then we're going to come up with the vocabulary word. Okay, so the first one in the picture, you can recognize this as a cube. The definition is a solid that is bounded by polygons that has a single region of space. So the word that we use for that sounds a lot like polygons. We call it a polyhedron. Alright, and now let's take a look at the polyhedron. It says a flat side of the solid that are polygons. So we're talking about this flat side here, that's a rectangle. We're also talking about the top flat side, that is a pentagon. This side over here, the left side, the right side, that back right side, the back left side, and the bottom, they are all called, so let's go ahead and point to one of them. These are all called, it's a face. These are faces. Alright, the line segments formed by the intersection of two faces. So when this rectangle here and the bottom rectangle, or I'm sorry, the bottom pentagon, when they meet, they form this line segment. That line segment is called an edge. I'm going to go ahead and highlight this one over here. It's an edge. The corner or point where three or more edges intersect. So here's one here. That's called a vertex. The two faces of a prism or cylinder, or the bottom face of a pyramid or cone. It is the polygons used to name the polyhedron. Okay, so we give the top and the bottom, or the bottom of a pyramid, a special name. We call that a base. Okay, so this one here, this top one, that's a base, and this one down here, that pentagon, that's a base. And usually a base is a non-rectangular face. If the shape has a bunch of rectangles and a couple of non-rectangular shapes, the non-rectangular shape will be the base. A polyhedron whose faces are all congruent. Regular polygons. Well, if they're regular polygons, then it's a regular polyhedron. So, regular polyhedron. A polyhedron such that any two points on its surface can be connected by a line segment that lies entirely inside or on the polyhedron. So what that means is that it doesn't matter what face you set this on, you can turn it over, and if you put it outside and it's raining or you pour a cup of water on it, the water will fall off of it. If there's any surface that curves in, then the water, where the water can collect like a cup, then that's not this shape. So what we call this, since all the water would run off of it, we call this a convex polyhedron. If it was concave, that means it would be like a cup and water would pool at the top. So if you ever see something like that, that would be concave, but we're just going to study convex polyhedrons. Okay, the next one we call this platonic solids. And some people pronounce that platonic solids. Okay, we're going to just study 5 of them. There's a bunch of them, but we're just going to focus on 5. 1 of 5 regular polyhedron, a regular tetrahedron, that's this over here, or a cube, that's this one here, or it could be an octahedron or a regular dodecahedron or a regular icosahedron. All right, so those are the ones that we're going to study, and we'll get to those in a minute. The next one says, if you look over here, we've got this pyramid here. We've got a plane that's going to cut the top of it off. And if we were just to take that top piece off and look at where the knife touched, that would be the intersection of the plane and the solid. We call that a cross section. All right, now there's a lot of pages to these notes, so you want to make sure that you number these pages. This one here is page 1. All right, next. All right, here's our platonic solids, the platonic solids. Okay, so here, this one was the tetrahedron. And notice how this one is made of all the same shape. It doesn't have a combination of two different shapes to make it. These are all triangles. And this is made with the 1, 2, 3, and then the bottom side triangle. Another name for this one might have been triangular pyramid. Okay, the next one here, that's a cube. You've been studying this one for quite a while. This one here, if you look at the way this one's formed, it's all triangles as well. There are 4 triangles on the bottom and 4 triangles on the top. So that makes a total of 8 triangles. So yes, this one is the octahedron. Okay, this one is made of all pentagons. So here we've got 1, 2, 3, 4, 5. And then on the back side there's 1, 2, 3, 4, 5. And then you've got 6. So 1, 2, 3, 4, 5, 6. And then on the back it looks the same. 1, 2, 3, 4, 5, 6. So that makes a total of 12. And remember, 12 sides, that's dodeca. So dodeca, D-E-C-A, supposed to be C, D-E-C-A, hedron. Dodecahedron. Okay, and this one, that's going to be very hard because we have just a picture to look at. This one we call the icosahedron. And again, it's made all of the same shapes. It's all made of triangles. All right, now I want you to take a look at the types of solids. I've put a couple of polyhedras over here, and over here, these are not polyhedras. Take a look at the difference between the two. You should quickly notice that these do not have curves. No curves. And these over here, they all have curves. If it has curves, then it's not a polyhedron. All right, now the next one down here is a theorem. This is pronounced several different ways. I was taught to pronounce it Euler's theorem. Some people pronounce it Euler's theorem. So Euler's theorem is the number of faces vertices and edges. Now, in some of the problems that we do in the future, we're going to have to count up how many faces does this have, how many vertices, how many edges. Well, what Euler's theorem does is it helps us make sure that we haven't made a mistake in counting. So what we know is that the number of faces, vertices, and edges of the polyhedron are related by this formula. F stands for faces plus V stands for vertices equals E stands for edges plus 2. If you take the number of faces and add it to the number of vertices, that should equal the number of edges plus 2. And we're going to work with that in just a second. Again, this is, put your page number, this is page 2. All right, so now we have some examples. And some of these are going to be examples that I do, and some of these are going to be your check for understanding activity. So whatever I do not do, you're expected to bring to class completely done. All right, take a look at this shape here, and you're supposed to tell me, is it a polyhedra or not? Well, as simple as this. Does it have any curves? If it doesn't, then it's a polyhedra. This one has no curves, so it's a polyhedra. This one, no curve, so it's a polyhedron. But this one over here has a curve, so this is not a polyhedron. All right. In the next one, we're going to identify the polyhedron. We're going to find the number of faces, vertices, and edges, and then we're going to check our answer using Euler's theorem. All right, so first of all, I told you that the vocabulary term that we just talked about, base, it's the two faces of the prism, and usually there are the non-rectangular face. Okay, so here, I want you to add that right here, that the base is usually the non-rectangular face. And the base is where we get the name of the shape. But in a situation like this, where they're all rectangles, if you look at the top and the bottom, the front, the back, and the side, they're all rectangles. So the only way to name this one is rectangular prism. Let's go ahead and name all of them. Number 5 here, this one, these are all, if you look at them, they're all rectangles all the way around. But the front and the back, those are going to be 1, 2, 3, 4, 5, 6. Those are hexagons. So this is called a hexagonal prism. So you put the word hexagon, add the letters AL, hexagonal prism. It doesn't come up to a point, so that means that, and it has two bases, so that's a prism. All right, this one here, the non-rectangular shape, that would be the triangle. So this is a triangular prism. This one here, we just learned about this one. This one has a special name. All the faces are the same. They're all triangles. So this one is a tetrahedron. This one, notice how it comes up to a point at the top. This one is a pyramid. And you look at the base to name it. And this one is a square. All of these sides are the same. So this is we call a square pyramid. Okay, this one of course is a cube. This one here, you've seen this one before. This one was the 8 sides, so this is the octahedron. And this one you saw on the previous page. This is the dodecahedron. Okay, now let's go back up to the top and we count. Faces. How many faces does this have? Well, it has a top, it has a bottom, it has a front side, it has a left side, and it has the front, and it has the back. So it has 6 faces. Now we're counting the corners. There's 1, 2, 3, 4 on the bottom, and 1, 2, 3, 4 on the top, so that would be 8. The edges are the segments. There's 1, 2, 3, 4 on the bottom, 1, 2, 3, 4 on the top, 1, 2, 3, 4 around the lateral surface area. So that's going to be 12. Alright, so now to make sure that we didn't leave anything out, we're going to plug it into Euler's theorem. So we take our faces, which is 6, and our vertices, which is 8. Then we say 6 plus 8, does that equal 12 plus 2? Well, 6 plus 8 is 14. When you add that together, that's 14. When you add that together, it's 14. If the left matches the right, then you counted the correct number of faces, vertices, and edges. All right, folks, you're going to do the rest of this page by yourself and bring it in. This is page 3. All right, the next one. Up here at the top, don't miss this one. This is still Euler's theorem. It says, is it possible for a polyhedra to have 16 faces, 34 vertices, and 52 edges? Explain. Well, we're going to use Euler's theorem to explain that. So we're going to say 16 plus vertices, which is 34. Does that equal 50 plus 2? Well, if I add these together, I get 50. And if I add these together, I get 52. So those are clearly not equal. So the answer is no, and it's because it fails Euler's theorem. All right. Okay, so now we're going to refer to the isometric front view of each figure that is made of cubes. So here we've got these pictures, these cube pictures. And it says, draw the top, the front, the side views of the figure. Then then answer each question. Okay, so the top view, that means looking straight down on top of it. So if I look straight down, I've got 1, 2, 3 squares, and then 1, 2, 3 squares. So that's going to be, I'm going to draw a big rectangle. I'm going to cut it in half, and then cut it in thirds. So it's going to be a row of 3 and a row of 3. Now the front view, if you look just straight on to where you can't see the right or left or the top or the bottom, just straight on, it is 1, 2, 3, 4, 5, 6, 7, 8, 9. It is 9 squares. So that's what the front view looks like. Okay, now if we look at it over here on the side, it's going to have 3 stacked and then only 2 stacked. So I'm going to draw 3 stacked and then 2 stacked. So that's the side view. And then answer the question, how many cubes are in the figure? Well, there's 3 back here, 3 back here, and 3 back here. That's 9. There's 2 here and 2 here, so that's going to be 10, 11, 12, 13, plus 1 here. That makes 14. How many faces are in the top view? 1, 2, 3, 4, 5, 6. Okay, so what you're going to do is for 14 through 16, you're going to draw the top, front, and side views, and then you're going to answer the questions. All right, folks, this is page 4. So you're going to do the rest of this for your check for understanding, and you're going to bring it in. Okay, so on this next one, okay, it says, various orthogonal views of cubes are shown below. The edge of one block represents 1 unit in length. A dark segment, the dark segment, indicates a break in surface. That means that it's like a stair step. There's going to be, they're not at the same level. Using cubes, make a model of the figure. Draw the back view and answer the question. So you can use graph paper to make cubes, or you can come in and use cubes, or if you have blocks at home, what you're going to do is I always like to start with the front view. So I place my blocks and I make my front view match. Okay, then I check it to the left side of it. That means looking over here. So I check, dump it over on the left, and I say, does it look the same as the left view? And it does. Okay, and then I look over here, turn it over to the right. Does it look the same? Yes, it does. Now there's that thick line, so remember there's a stair step right here. Okay, then you look from the top. Does it look the same? Good. Okay, so now this is the front view, so if I want to look at it from behind, I have to flip it over. There's the rear view. So they want us to draw the rear view. So I'm going to draw 3 and 1. Okay, so that's the back view. And then how many cubes are used? 1, 2, 3, 4. That's 4. Okay, so I want you to try these two on your own, and then bring those in so we can discuss them. All right, the next one, folding cubes. Now, you're going to need a piece of graph paper for this one. And I happen to have this piece of graph paper here. And what I'm going to do is I'm going to use this graph paper and I'm going to recreate this shape here. And it says, write the missing letter so that when the pattern is cut out and folded to form a cube, the letters will align and spell cube. So we want to place a B somewhere in here so that when we fold it up, the cube will go all the way around. Alright, so to do that, I'm going to use my graph paper. Alright, so I'm going to have 1, 2, 3, 4. So I'm going to draw this a little bit bigger. I'm not going to use little teeny tiny squares because then it'll be hard to fold. So that's that bottom square. Then 3 by 3. That's this one. And then 3 more. 3 by 3. Okay, and then over here, this goes out here, and this is the U. And then one more up here, and that's the C, and then over here to the left. And what we're doing is we're drawing all squares. Okay, so now I've recreated it. Now I'm going to use my scissors and cut it out. And then after you cut it out, you want to fold it up so that you can try to figure out where the B is going to be. And it's not just going to be straight up, it could be tumped over on its side, it could be upside down. So you're going to have to figure out not just which face the B should be on, but how should it be drawn on there. Okay, so here's my shape, and I'm going to fold it up. Okay, so if I fold it, and if I wanted to, I could tape it together, but here's my cube. And it's got the C here. If you turn it this way, there's the U. So the B should be right there. So I am going to flatten it out so that I can write my B right here. So now take a look at it. The B is actually on this face right here, and it's upside down. So there's the B. Should be upside down. Alright, I want you to do 21, 22, and 23 by yourself. And I suggest using graph paper. Okay, so this one is page 5. Okay. And now the last page. Cross section. Describe the shape formed by the intersection of the plane and the solid. So here we have a sphere, like a big ball, and this plane is coming in and it's cutting the top off. If we lift that up and look at it, what shape did that plane touch? If it was a knife, what shape did it make? The cross section would make a circle. Okay, I want you to do 25 and 26 by yourself and bring them in, and of course this is page 6. Alright folks, that's it for your notes 12.1.